All right, welcome back to Chris Akers' second lecture. Take it away.
Thank you, Brian. Okay, so a quick recap of what we saw last time. We motivated ourselves to think about bulk reconstruction because we want to solve the problems of quantum gravity. And we want to use holography to do it. And we saw a little bit of the history of how bulk reconstruction has been understood. So, fundamentally, there's the extrapolate dictionary, which relates bulk operators near the boundary to CFT operators. Very nice, very fundamental, but not explicitly useful for reconstructing things deeper in the bulk, where there's a lot of interesting physics, like the interior of black holes. So then we saw how people push this a little further. They used the extrapolate dictionary to derive what's now called the Hkl Reconstruction Scheme, HKLL. And that basically has this, it's not clear how generally it works. It doesn't seem like it always works inside of black holes, for example, because of the singularity. But it at least has this nice form when it does work, where you can write a bulk operator as some sort of Green's function solution involving boundary operators. But it doesn't do everything we want, so we are motivated to go further and learn the limits of what we can and can't reconstruct in principle. So people thinking about this for a long time eventually converged on this very impressive theorem. Now, this theorem is, we're going to be able in this lecture series to go beyond this theorem, but it's very impressive. It does operate in this special case where we have restricted our attention to a certain subspace of the bulk that we're calling a fixed QES subspace. So we're restricting our attention to, say, vacuum ADS and order 1 matter excitations on top of that. And in this regime, we shouldn't expect the quantum extremal surface of some boundary region generically to move by more than order a Planck length. So it's roughly always in the same position. And it's in this context, with our attention on these sorts of bulk subspaces, that this theorem applies to ADS-CFT. And what this theorem says is everything that the quantum extremal surface formula has to tell us about bulk reconstruction, right? Because it says this formula, which is essentially the quantum extremal surface formula, right? You compute the entropy of a boundary region, and it equals some bulk region's entropy plus this A term, which I still haven't defined for you, but will do shortly, and morally, when applied to ADS-CFT, is like the A over 4G of the quantum extremal surface. It says this statement is equivalent to this reconstruction statement where some operator acting in some bulk region, the one inside the QES, can be reconstructed in the sense of this equation by an operator acting on capital B. And ditto for operators in little b bar being reconstructed on capital B bar. Okay, so this is great. It tells us everything the QES formula has to tell us about bulk reconstruction, which is a lot. But admittedly, in this special context of fixed QES subspaces. So let's see the proof. The proof is the most technical aspect of these lectures, but I think we will be able to get through it. And my hope is that it will show you how this sort of thing is proven so that you can help push the boundaries, right? So at the end, you're going to see that we're not done with this program. We're not done understanding bulk reconstruction, and we need people like you to come in and help prove the more general theorems we need. Okay, so the main tool of the proof we introduced last time, and then we stopped. So the main tool was that there's this operator that acts on little b, that does the following in general. So if it acts on the state psi, little b bar, so psi is a state on just H code there with the two subsystems little b bar, it maps it to this state, where essentially what it's done is it's brought in some two copies of little b, which we called little a and little r. They were maximally entangled, and then we swapped little b and little a. One thing to note is that this W is an isometry. This will play a role later. An isometry is this thing, it doesn't change inner products. Right, so if I have two states, psi and phi, on, say, little b bar, if I were to insert, if I were to change phi to W b phi, and if I were to change psi to WB psi, then this inner product would change to psi WB dagger, WB phi. And you can confirm from this equation that W dagger times W is just the identity acting on little b. So it's just the identity. And so this just equals psi phi. W doesn't change inner products. It's an isometry. That's what that means. And that will play a role later. Okay, so this is the main tool of the proof. Yes?
So psi and phi are states on little b and little b bar.
That's right.
But WB dagger, WB is just the identity on little b, not on little b bar.
Yes, thank you. So whenever I write WB, what I really mean is WB tensor the identity on all the other systems. And so this would actually end up being the identity on both. Yeah. Yeah. Thanks for the question. Okay. Good. So now we're going to use this fact to prove that the first statement here implies the second statement. So we're going to prove that if you can do this sort of reconstruction of little b, just using capital B, then the entropy of capital B equals this. And then we'll prove the converse afterwards. Okay, so the first thing to recall was, we knew a little bit more about WB than just that it acted this way, right? Fundamentally, it involved this swap operator. And the swap operator, remember, was something like, if it swaps systems A and B, it morally looked like some normalization factor out front, and then a sum over essentially Pauli operators on A, and then Pauli operators on B. So these sigma i's, like sigma 0 is the identity, sigma 1 is like the Pauli X, sigma 2 is Pauli Y, sigma 3 is Pauli Z. So this was this would be, so if little b was just one qubit, then this would be exactly the swap operator between little a and little b. Now, to prove 1 implies 2, the main thing we do is we use the fact that 1 guarantees the following. That if there's some Pauli operator acting on little b, say on any state psi, right? Psi is, of course, a state in little b bar. And then you acted with v, that there exists some operator acting on capital B such that this equation holds. I don't know, I'll call it sigma tilde or something. Like this guy acts on capital B. Maybe I'll write a capital B here. But so this is the reconstruction of this Pauli. That's what condition 1 guarantees. And so that allows you, if you just now define, I don't know, S tilde in the following way, it'll be the reconstruction of this swap. So you don't change anything about how it acts on A, but now you change this guy to the reconstruction. So this is some operator that acts on little a and capital B, and then what it does is swap little b out. Okay, so what do I mean by that? I mean basically this. This S tilde acting on V psi. So if this is AR, this is like we've introduced this maximally entangled state between these two copies of little b. And then we act S tilde on it out here. That's the same as if we had acted this swap on A and B. Is that clear? Like we're just using one to say that instead of like this swap operator that swaps little a and little b, we could write it as an operator that acts on capital B instead of little b. Because we can reconstruct any operator that acts on little b. Let's do that. So the grand upshot of all of that is that assuming this condition 1, there exists this W, what we call W capital B, or we can call it W tilde capital B if you want, that reconstructs this W little b. So 1 implies that this guy exists. It does the same job. So it's some operator acting on capital B that does the same job. And you can also prove that it's an isometry. So just like we saw little b was an isometry acting on little b, sorry, W little b was an isometry acting on little b, this is an isometry acting on capital B. Yes?
Is there a reason that when you first introduced the main tool, the maximally entangled state was with B and R, and then when you defined S tilde, it was A and R?
Yeah, thanks. So, good, yeah. So, in this equation, I have done the full action of WB, which I think of as conceptually divided into 2 steps. In the first step, I should draw this here. So yeah, if you act WB on psi, so WB was defined as you introduce first this maximally entangled state on the 2 copies, little a and little r, and then you act the swap on little a, little b. And so, so this equals swap on little a, little b of psi BB bar. This is also BB bar. Max little a, little r. And this was this halfway step is what I was writing here. And then if you finish acting the swap, then you get psi of little a, little b bar, max of little b, little r. And that's this full equation. So yeah, I just written the halfway. Okay. Okay. So for proving 1 implies 2, the whole deal is showing that there exists this WB from the assumption of 1, and also that he's an isometry. And he is an isometry, maybe you see it, because it's the same argument that we had for W little b, but I leave it as an exercise to you to prove that. And we did all of this because what we want is to just compute now S of capital B in the state V rho V dagger, right? So condition 2 says we're computing the entropy of capital B in V rho V dagger. And this equals, by definition, minus trace of rho B log rho B. Now, here's the important thing. Before I continue this calculation, let me say I sort of neglected talking about little b bar, but the assumptions up here in 1 are completely symmetric between the unbarred and the barred b's. So everything I said also holds with the barred version, so let me write it out here. So it's also true that there exists a WB bar, like on capital B bar, you can reconstruct something that looks exactly the same, but for little b bar. So I'm also going to use this fact. So condition 1 guaranteed that both of these operators exist. We can reconstruct this guy here and this guy there. Question?
Hello. I am just trying to understand that part. So where there is the A tilde defined, the A is inside bulk, right? The small a is inside bulk.
Good. Small a is, yeah, like a copy of the bulk Hilbert
Yeah,
space.
exactly.
Yeah,
And capital B is on the boundary.
that's right.
So what will be the sum run on? So I is equals to what?
Yeah, so here in this exact equation, I was making a simplifying assumption that we're dealing, like little b was just a single qubit. In general, that's not important. It can be much larger. But if it's 1 qubit, then you just need it to run over all the Paulis, which so maybe I equals 0 to 3, where sigma sub 0 is the identity and sigma sub 1 is the Pauli X matrix.
Okay, I see. Sorry. So it is just a sum over all the Pauli matrices for one single qubit.
That's right. That's right. And it's the same Pauli matrix on the two systems. And what's cool, and you should work this out, that this actually implements the swap between the two qubits.
Yes,
Yeah.
Sure. Thank you.
Yeah.
For the clarity.
Okay. So here's an important fact about von Neumann entropies that we're going to use in this proof. This, right, so this state here, V rho, V dagger, that's a state on BB bar, these two systems, capital B bar. And we're computing the entropy of one of those factors, B. This quantity doesn't change if you act isometries on either B or an isometry on B bar. If you acted some general operator on both of them together, you could change the entropy. But if you act an isometry just on capital B, won't change it, or just on capital B bar, won't change it. Let me prove that to you. Okay, so what happens if you act some isometry, right? Like let's just assume we have K, which is an isometry. Right, remember this is equivalent to saying that K dagger K equals the identity. So if K is an isometry, let's act some like K on B bar. How does that change this guy? Well, where does B bar even show up? I guess he sort of shows up here in the row B's because row capital B equals the trace over B bar of V rho V dagger. And okay, if we're acting some K on B bar, what does that mean? That means that we're inserting here, so we're inserting here some K on B bar and some K dagger on B bar. But this doesn't change row B because by the cyclicity of the trace, you can just pull this K dagger around. Right, so this equals like K dagger K, V rho V dagger. And then this equals the identity. And so it's like we never inserted K on B bar at all. Quick quiz. Why don't we just say the same thing about V? V was also an isometry. Why don't we just pull it around and have it cancel V there? Any ideas? Exactly. Yeah, so V maps little b bar to capital B bar. So it's not just acting on the one system we've traced out. That's important. Okay. K, on the other hand, acted just on the system we traced out, so it doesn't change anything. Okay. Okay, so we've concluded that KB bar doesn't change S of B. What about K of B? An isometry on B, does that change S of B? Maybe, it seems like maybe it could, right? Because how would we take this formula and insert K acting on B? Well, I'm going to erase this. We would get we would send it to minus trace of KB rho B, KB dagger log KB rho B, KB dagger, right? This is in the log. Right, so to get this, all we did was take that up there, that formula, and then we just replaced rho B's with rho B conjugated by K. Okay, so why isn't this different? Right, so it doesn't seem so easy to cancel all the K's. There's K's inside the log. The reason it works is that I claim this log of K rho K just equals K log rho B, so KB log rho B, and then on the right-hand side, KB dagger. And the way to prove this to yourself is to Taylor expand out this log, and then you get polynomials in the argument. And all the polynomials, it'll be the argument to some power. And the K dagger Ks and all of those powers will then cancel each other. So the only Ks and K daggers that remain are the ones that stay on the outside. And so then you can just undo the Taylor expansion, but now with a lot of K's canceled, and then you get this. Okay, so this is something you can prove. And then now it's clear that the K's cancel, right? So this guy and that guy make the identity by the cyclicity of the trace, because we're tracing over everything, right? You can pull this guy around, he cancels this guy. Then we just got back trace of rho log rho. So KB also doesn't change S of B. All right. So isometries acting on either of the two systems doesn't change the entropy. And therefore, we can say the next step, which is following. Sorry, I'm erasing the first part of the. So, okay, so now we can say the following. S of capital B, V rho, V dagger. This is what we're trying to compute. And I claim, from what we've seen, that it just equals S of little a, little r, capital B in this following more complicated state. So I apologize, it's going to look nasty, but all I'm doing is taking V rho, V dagger, and then conjugating it by these isometries that we constructed. And the system changed here from B to AR because we acted, right, whenever you act in isometry on capital B, like you map it to a larger Hilbert space, what needs to go here is the Hilbert space you mapped it to. Does that make sense? So WB, right, mapped like HB to HB tensor H little a tensor H little r. So I wasn't very explicit about this in this proof, but for the entropy not to change when you act in isometry, the system that you're computing the entropy of needs to be the image of the isometry. Or you have to if you're acting the isometry on this system, you need to put the image of the isometry here. Okay. So I'm going to erase this actually. Okay. Thank you.
Quick question. Do
Yes.
we also not need A bar and R bar there? Because
Thank you. So good. So we don't need the A bar and R bar because those guys showed up from this operator, which disappeared whenever we. So in this formula, they're gone by the time we get to row capital B, because they showed up here, and so technically when I acted this isometry here, the trace then became over B bar, little a bar, or if this was the W capital B bars, the trace becomes over B bar, A bar, R bar, and then they get traced out. Okay. So we're almost done with this 1 implies 2 proof, because the fact that these two are equal was from that argument. The isometries don't change anything. But then now we're going to use condition 1, which, as we saw at the very top of that board, was just the statement that this entropy equals S of ARB in a different state where you pull the W's into the V. Right, so now it's just V, W little b bar, W little b, rho. So I've used condition 1 here to say that these guys reconstructed these guys. This state you can write out explicitly if you use this and the equivalent form for W little b bar. You can, I claim, write this out explicitly, and what you'll get is that this equals rho on little a bar. Rho is the state here, the one we started with on little b bar. Tensored with some stuff. And the stuff doesn't depend on rho. I might call it chi, but I'm going to write it out for you explicitly. So it's just like V, and then max on little b little r, tensored with max. This is like the density matrix of the maximally entangled state on little b bar, little r bar, V dagger. Okay, so what's important is there's no rho dependence there at all. It's just some state. We could call it chi. Some density matrix.
Small question.
Yeah.
Should there be tildes in the W's in the first subscript? in this one?
Yes, yeah. I guess we have been using this notation where the reconstructions have tildes, so there
So
should be
they're the
tildes.
reconstructed one.
Yeah, these were the guys that reconstructed these guys. That was the step from here to here. Then now we just saw, using this formula, you can just explicitly compute what this is. It's this thing, which maybe looks nasty. So you're just like, what have we gained? What we gained is that now this is actually something that you can write down. So S, like the entropy of these three systems in this state, we know what it is. I don't want the board to be too messy, but it's it equals, first of all, it equals S of little a in the state rho, right? Like, so now I'm just actually saying, what is the entropy? Well, this state was some factor, some product state. The entropy of that is like the entropy of one of the factors plus the entropy of the other factor. So the A part here is that guy, he just contributes this S of A in the state rho piece. And there's going to be another piece. But remember that little a is just exactly what little b was in the state rho. So if I want to talk about the original state, I could just say that's the entropy of little b in the original state row we started with. Okay, and then this extra piece is this entropy of capital B, little r, in this chi state. Chi was this mess. But it didn't depend on row, so that was the important part. And this is the thing that is called A, this like row independent piece that plays the role of area. So this is like the definition of area as far as this theorem is concerned. And then that's the proof of 1 implies 2. So now we have explicitly just used 1 to compute the entropy of capital B. All right. And that's what I'll say about 1 implies 2. Yes.
Can you please just say again how we got the row A bar factored from the rest?
Yes. So the way it worked was, I'll leave part of that as basically an exercise for you to just look at, take this state where row is arbitrary, and then just try and conjugate it with these W's. And the reason why, when you do that, you get this little a bar piece that's factored from the rest, is for the same reason that it's just when you act W on some state, right, there's this part where little a goes and this part where the rest goes. Does that make sense? So it's like this factor was this one, and then this factor was this one. And that's like just what W little b did. So this theorem, it kind of gives some intuition for why the QES formula works, or what it's doing. Right? This W has taken the state that you had, the state on capital B bar, and it's extracted it into 2 pieces, one of which just had the bulk state, and one of which was all this extra stuff that depended on V, but not the state. And that's morally how you might think of the area. Okay. Okay. So let me tell you the idea of 2 implies 1, because maybe this is the one that is more interesting, because it tells you how you start from the QES formula and then you prove that you can do some reconstruction. Yeah.
Just if you can, sorry, I think I missed, how can you interpret that SBR as an area?
Good, yeah, so the reason, okay, so in one sense, I'm tempting you to interpret it as an area by just saying, let's call this A. But really it's just some entropy of some part of the state. But the reason why it's nice, it might admit this area interpretation, is that it's a piece that doesn't depend on row here, right? So it's like the most important feature here is that these entropies just, they add together. So just like in the QES formula, you got this area piece and it added to the bulk entropy piece. That same thing happened here. And so you get this extra piece and it's some feature of the code. It doesn't depend on the state row. Okay, and there are other reasons why it nicely matches what you might expect from area. And that is, for example, if you were to now compute S of B bar, like capital B bar. So I showed 1 implies 2 for the unbarred systems, but you can also show this, like that the entropy works out for the barred systems. And if you did that, then you would get the same exact A there. But I mean, this first term would be S of little b bar. But you get the same exact A. And that's exactly what you expect of the QES formula, where you take 2 complementary systems on the boundary, compute their entropy using this QES formula. And the area is the same because the QES for both of them is the same. It's the area of the surface, the same surface that divides the 2 entanglement wedges. And so for that reason, it's kind of nice because it's the same area showing up in both equations. Yeah.
Sorry, just a question, but if you now chose to redivide the boundary, for example, and now B had like twice the size or something like this, would these terms scale correctly? I know that the first one would also change because the interior would also change. But
Yeah, you're saying like pick a different boundary region.
Like, I don't know, you double the size of the area that B is covering.
Great,
Would it like, it's not up, because of that little r, which is sort of a copy of big B, right? Sorry, of little b. It doesn't look like it's just gonna double. I don't know.
Yeah, so good. So this theorem is about one particular division of the boundary. And what you want is something I also want, which is a theorem that has more to do with all boundary regions simultaneously, right? Like, that's not what this theorem says, though. This theorem is a statement about what you can, like you divide the boundary into two, and then it gives you a statement about that division. And how that relates, like how the A of this division relates to like A's of the other division, is not anything promised by this theorem. Yeah,
okay.
that is an interesting question, but not discussed here at all.
Even though in the quantum extremal surfaces perspective, we know that it works fine, right?
Right, yeah, in the quantum extremal surface, yeah, in ADS-CFT, there's a quantum extremal surface for every boundary region.
So we can, yeah.
That is true, but yeah, in some strict sense, logically independent from what we're trying to show with this theorem here. Yeah, but how all the different QESs relate to each other, because they're all surfaces in the same geometry. So if you change the geometry at one point, it changes like multiple different QESs. That's not captured here. It's not trying.
Okay,
Yeah.
sorry, okay, thanks.
Yeah. Okay, so to prove to you that 2 implies 1, we have to do a few tricks. So one thing is that I need to introduce to you a state that I'll call phi, which is basically a maximally entangled state, but between little b and little b bar, and some other extra system that I'm going to call capital R. It's some reference system that doesn't, it's just extra. And the state is this one. It's just the state where you've maximally entangled little b and little b bar with R. So we're summing over I and j, where I is a complete, like index is a complete basis for little b, j index is a complete basis for little b bar. R is big enough to fit into a state like this. And what we're going to show is that, okay, so this is a tool we're going to use. And we're going to show that for all Pauli matrices acting on little b, there exists some unitary acting on capital B that reconstructs that Pauli matrix. Now, and it reconstructs it. What we're going to show is that there exists a unitary on capital B that reconstructs this Pauli matrix on little b when acting on this particular state phi, this particular one right here. Now, this seems a little weaker for 2 reasons than what we seem like we want to show, which is that for all operators on little b, not just Pauli's, but for all operators, we have a reconstruction, and it works on all states, not just this one state phi. But actually, it's they're the same. These statements are actually equivalent. And the reason why it's enough to, okay, the reason why reconstructing on phi is enough to reconstruct on all states psi, it's essentially because so you can just take this formula, if it's true, and then you can just derive that it's also true for all psi. So you can just convert phi to psi. And the way you would do that is essentially you would act on both sides with some psi bar. This is the complex conjugate of psi. Psi bar on the system R. So I'm going to explain this in a little bit more, but we just took the state UB v phi, and then so actually before you imagine acting this bra, I have this formula I wrote up here, right? This one that we're assuming for now, and we're going to derive it for all psi, and then now act on both sides with psi bar on R. Psi bar is the complex conjugate of psi. Psi is the state we want to prove this equation for. Like, what do I mean by complex conjugate? I mean, like, let's say psi was sum over I of some coefficients I. Psi bar is literally, you just complex conjugate all the coefficients. Okay. And what happens here, once you act on both sides with psi bar, is that this, like U, B, and V have nothing to do with R. So you can just commute this guy through. So you just go straight through, and then you get psi bar phi on both sides, and then UBV acting on it on the left side, analogously for the right side. And then you just use the fact that psi bar phi equals psi on little b bar. So, right, phi is a state on little b bar r, psi bar is a state on r, and then I claim that this gives you psi on little b bar. I'm not going to prove it for you, but using this, you can work out as an exercise that this is true. Okay, so this is, you could say, a trick or just a hack for just showing that it's sufficient to prove this if we want to get this. Okay, so essentially what we're going to show is that for all Paulis, there exists a unitary on capital B that reconstructs it on all states. That's still a little weaker than what we want because we're talking about Paulis and not all operators. But actually it's enough because Paulis form a complete basis for the operators, right? Like, you can take any qubit operator you want and you can write it as a linear combination of Paulis. If you can reconstruct those Paulis exactly, then you can reconstruct any operator exactly. So I'll just say that, and then we can talk more about it if you would like. But it's sufficient to reconstruct the Paulis perfectly well to reconstruct any operator perfectly well. Okay. Good. So I'm going to box this because this is where we're going, and then I've argued to you in a way that maybe convinces you, or maybe you get the vague idea that that's going to be sufficient to imply 1. And then there's one more little lemma that we need. This one's cool. It's a quantum information-y lemma. Some of you may be familiar with it. Some of you, this will be a good lesson. The slogan of this lemma, yes?
So the statement that having all the Paulis is enough to reconstruct any operator, is that relying on the fact that we have like a finite dimensional Hilbert space or something? Is that true for all?
Yeah, I'm for simplicity talking about, I'm imagining little b is just made up of a finite number of qubits.
Yeah.
I could analogously prove this without that assumption. It would just be a little bit harder, like technically, to show on a blackboard, yeah. But, yeah. Thanks. So, the slogan of this lemma is that if you have some mixed state, you can always find some purifying reference, right? So you can find some, if you have some rho, you can find some psi, some pure state psi, that includes a reference that purifies it, so to say. And if you were to trace out the reference again, you would get back row. So that's what it means to purify this row. But that's highly non-unique, so there's many different size that could purify any given density matrix. But you can prove that they're all related by a unitary on the purifying system. So that's the slogan, but I'm going to write down precisely what I mean, what we need. So let's call omega on BR. So this is going to be some density matrix on capital B bar R. Let's say that that is the state you get by, you start with this phi state up there. Then you map it with V. So this is a state now, so phi was a state on little b bar R. Act V on it. Now you have a state on capital B bar R. And then now we're going to trace out capital B. So we just have a state, some mixed state in general, on capital B bar R. Okay. And then I'm going to make your notes as hard as possible to write, I'm going to use Xi as the next density matrix. And it will be very similar to this, but instead of being exactly just phi, I'm going to start with phi, but act some arbitrary Pauli matrix on little b. So this is like a state you would get by starting with that state, acting some Pauli matrix on little b. And then map it with V, and then trace out B. So the only difference between these is that before we mapped it with V and traced out capital B, we acted the Pauli on little b. Okay. So one thing that you can prove, and I'm not going to have time to prove it for you, but you can see the proof in, say, Nielsen and Chuang, or Watrous. I like the book Watrous, Quantum Information Theory. Is that if omega equaled Xi, right? I mean, you might think that how can they be equal? They're sort of different. Like I put a Pauli in here. Well, it's okay because I mean maybe they're this state could be different, but not different when you trace out part of the state. Okay, so it's possible that omega equals Xi when you're looking at B bar R. If that's the case, it implies there exists a unitary acting on capital B such that UB V phi equals V sigma B phi. Okay, so this is the precise statement that I'm going to use. I claim that this is a corollary of a famous theorem in quantum information theory. And the basic reason is that V phi is a purification of omega, and V sigma phi is a purification of Xi. Okay, so if this blackboard seemed a little fast, just know that this is true. I'm not going to be able to prove it to you in time, but that's the statement that we're going to use. Okay. Now, I want all of these blackboards. I don't want to erase any of them, but I'm going to need this one briefly, so I'm going to erase the statement of the theorem. Sorry. Yeah.
For this lemma, is it important that we're acting with the Pauli? It seems like it could work for any operator.
It would work for any operator.
Okay, cool. The Pauli will be important later, I guess.
Yeah.
Okay.
It would work for any operator, yeah.
Okay, thanks.
It's just sufficiently, yeah. It's in particular true for Paulis, that's why I said it. Okay, and then the rest of the proof goes like this. You say, consider the state phi. This is a state on B bar R. I'm going to stop writing B bars for the rest of this proof because they just go along for the ride. You just do everything that I do to little b, you can do to little b bar. It just makes it more complicated to write. So I'm just going to imagine that B bars may be trivial for the sake of this, but it just doesn't change anything. And then now, we know what happens if I act W little b on this. Right, you get the state phi little ar max little br. And if I acted V on both sides, what do I get? Well, V act here, and then V goes here. Right, I can write it after this guy, because V doesn't act on anything here, it just acts on little b. Okay, so this equation is true, it follows from things that you already accepted. And now if I were to take this state and then compute its entropy, so if I were being consistent with how I was writing things before, I would write this. Like, so I'm computing the entropy of this system and this state. But if you'll allow me, it's sort of redundant for me to write the second half of this. I'm just going to erase the second half. I hope that's completely clear. This is the state I have, and these are the systems I'm computing the entropy of. Okay, and I claim that we already, right here, saw that the entropy of this equals A plus S of B in the state phi. This was something that was true, just always, did not at all depend on 1, right? Like I say, we computed this up here, but not in the step where we used statement 1. That's important because I don't want to assume 1 to derive 1. Right now we're just assuming 2. On this board up there, 1 was assumed in the first step, but this fact being true was just this step right here, the second step. Okay. Now, I claim that the entropy of these 3 systems in this state equals the entropy of B bar R. So this state right here that I'm boxing is a state on 5 systems, right? Capital B, little r, little a, capital B bar R. And you can prove that anytime you have a pure state like this, the von Neumann entropy of some set of factors equals the von Neumann entropy of the complementary set of factors. You can prove that with the Schmidt decomposition if you're not familiar with that. Okay. So I'm just writing the same state. And then now, okay, so let me keep a running total of what we have. So I'm going to erase this second part here. To keep a running tab of what we've used so far. So we have that A plus S of B in the state phi equals this S of little a, little r, b, V W B phi, which equals S of B bar R in that same state. Right? Now, let's look at this state, this reduced density matrix. So we're going to take V, W, phi, and trace out everything but B bar R. So let's write that out. This step, you can just believe me because it's going to look like a bunch of symbols. All we're doing is tracing out, I'll write it this way, tracing out ARB from this state. which equals some normalization, 1 over d. D is the dimension of little b. Times some sum. You don't have to follow all of these details. I'm just writing the calculation out for you. But I claim, so at this step, going from this to this, I'm just plugging in the definition of W little b. Yes.
In this notation where you're not writing down little b bar,
Yep.
should I, like, if you're acting with W little b, for example, should I also think that you're acting with W little b bar?
Yep.
Just for example? Okay.
Yeah, do that too.
Like anywhere where there's a little b with something attached, I just also have the analogous object with little b bar?
That's right.
Okay.
Yeah. Okay. So you plug in what little W little b is, you get this thing. Okay. The trace over b is here. And then the trace over little a little r gives you this. And so this is like a correlation function between these two Paulis. And you can prove, because Pauli's acting on a maximally entangled state, generate a complete basis for those two systems. This equals delta ij. So I is which Pauli here, and then j is which Pauli here. So you can just prove to yourself that this gives delta ij. So you can perform the j sum that fixes these two Paulis to be the same. And then I'm going to do a horrible thing where I'm going to write the next line above. And so you just get 1 over d of sum over I, trace of b. And then I'll summarize this entire board by saying, okay, so if you want, just call all of this boxed thing psi I. So we have 1 over d times the sum over I of psi I. I runs from 1 to d, by the way. Okay. So over here, in our running tab of what things equal what, we have that, so we explicitly wrote out what the state is now, and I'm going to, again, sort of have an abuse of the notation I've been using. I'm going to now put the state in the argument of the entropy, just because it's an ugly state. So it's like the sum over I of 1 over d of these density matrices psi I. We're just evaluating the entropy of this state. And here is a QI theorem. This is an important QI theorem for this proof. This is greater than or equal to, so this is something also you can look up in like Nielsen and Chuang. This is greater than or equal to the sum over I of 1 over d of S of psi I. Okay, so it's just this is like the, what is it, the concavity of the entropy or something. Like, so you get the entropy of a mixture of density matrices. In general, that's greater than or equal to the average of the entropy of the density matrices. So the intuition, you can just prove this. I think Jeff mentioned it actually in one of his lectures, but the intuition is that the entropy of the average is just going to be greater than the average of the entropies, because there's some uncertainty about which state you have. And the uncertainty adds to the entropy. And very importantly, you can also prove that this inequality is saturated if and only if all the psi i's are equal to each other. So psi I would have to be independent of I. Okay, now the next thing is that, what does this equal? Well, here, so far we haven't used statement 2 of the theorem yet. Now we're going to use it. This S of psi I, if you look at psi I, it's a kind of state that is governed by statement 2, and you're guaranteed by statement 2 that this equals A plus S of little b phi. That's using 2, statement 2. What's important is that this doesn't depend on I. So you can do the I sum from 1 to d. That cancels this 1 over d. And you get that this just equals A plus S of little b and phi. Okay, here's the magic. So we've sandwiched everything, right? Because we started with a state with A plus S of b and phi equals all of this greater than or equal to this equals A plus S of b and phi. So this inequality in the middle has to be saturated. And because it's saturated, you know that all the psi i's have to be identical. Because all the psi i's have to be identical, right? So in particular, like the psi that corresponded to having the identity here, which we called omega, equals the psi that corresponded to having some other Pauli that's not the identity there, which we called psi up there. So they're equal, and therefore there exists a unitary that reconstructs it. Okay, so that's it. That's 2 implies 1. I know this used a lot more quantum information tools. It was probably technically the fastest of all of them, of anything in these lectures, but now you're exposed to the tools. Okay, so we've shown that we've proven the theorem. 1 implies 2, 2 implies 1. Great. Great. Okay. So we have the theorem. Now let's move on. Let's say the theorem was great, but it wasn't constructive. I think someone brought this up last time. It just shows that for any operator in little b, there exists an operator in capital B that reconstructs it. But what is that operator in capital B? It would be nice to actually have an explicit form for it. There are explicit schemes for this, and people keep coming out with more. The one I want to mention is one that you actually heard about earlier today, I believe, called the PETS map. And I'm not going to write anything explicit about it, but PETS map is very useful because it basically has these guarantees proven by given by the quantum information community long before quantum gravity people even thought that it might be useful. These guarantees say that if anything works to reconstruct, this will work. So it gives you a form for this operator O on capital B. Happy to tell you more one-on-one or after the lectures about what it would look like, the examples that people have written down where it does work explicitly. But for now, I'm just going to say that. So we've proven non-constructively with this theorem that there exists a reconstruction. The PETS map has these guarantees that if anything works, that'll work. So the idea is basically use the PETS map. Great. Now let's move on from talking about explicit reconstructions. And let me tell you something, a corollary of this theorem that's very important. And historically, it was understood before this theorem even came out, just from earlier work that was already sufficient to reveal this. So there's a very important implication. It's an implication of subregion reconstruction. So, right, so one thing that this theorem told us we could do is if there's an operator in little b, we can reconstruct it using just a subregion of the boundary, capital B. We didn't have to use the whole boundary. And maybe it's easy to take for granted on its face, but it actually has dramatic consequences that are very important for understanding the emergence of space-time and what these operators can do. And actually, before I say it, let me set up the stakes. So the stakes are, we proved before that, at least in this limited context of fixed QES subspaces, you can use capital B to reconstruct operators in its entanglement wedge. And maybe you can do it explicitly using the PETS map. And now you can ask, are we done? Are we done with the whole program of bulk reconstruction? We reconstructed these operators at the PETS map. Maybe those are just the bulk operators. Like, sure, the theorem only guaranteed they worked within this fixed QES subspace, but maybe they work more generally. Nothing said so far that the theorem, that these operators we reconstructed didn't work more generally. So maybe we're done. Maybe we reconstruct the operators. They're the best operators we could ever ask for. There's nothing better. We don't need to look for any generalization of this theorem outside of fixed QES subspaces because the operators we get from it are already good enough to work on every state. Is this the case? You could ask. Are we done? And the answer is no. It's not the case that these operators, this theorem guarantees, work on all states. They won't work on all states, and we're going to prove that to you. So this is very significant. So it's going to tell us that if we want to go beyond this limited context of fixed QES subspaces, if we want to talk about black holes, for example, we need to have a more general theorem. Okay. Here's how you argue that. And the slogan for this, for the people familiar with it, is that we're going to argue that you need to think about these operators as only working in a so-called code subspace. So let's imagine we have a time slice of ADS-CFT. We have some boundary region B. Maybe it's this. Here's its QES. So we know that at least in these fixed QES subspaces, it works. We can reconstruct things inside the entanglement wedge, but not outside. So if there was some operator here, say 5x, we can't reconstruct it even in this fixed QES subspace on capital B. But we can on the complement, on capital B bar. That was the theorem. Okay. Now let's divide capital B bar again into two pieces. So let's say that this capital B was 1/3 of the boundary. And then we're going to divide the rest again into thirds. So we're going to have three pieces, A, B, and C, that will all be 1/3 of the boundary. Let's say we're talking about vacuum ADS, just for simplicity. So the diagram I'm going to draw is just symmetric here. So this is the QES of C, this is the QES of A, and this is the QES of B. So we agreed that B cannot reconstruct phi on its own, A cannot reconstruct phi on its own, and C cannot reconstruct phi on its own. But we also agreed that any two of them can. So if I took B and C together, we could reconstruct phi, because this would be its QES over here, and this would be inside of it. So no one can reconstruct phi, but any two can. And this is a big deal. right? So you know, that fact might not be surprising so far. You're like, okay, I accept that. There's subregion reconstruction. But it has an important implication. So let's say the reconstructions have the following names. So let's say that the reconstruction of phi that you get on AB, we're calling OAB, sorry, OAB. And the reconstruction you get on BC is OBC, and likewise on AC is OAC. So are these the same operator in the CFT? That's a question I'm asking you now. This is going to be an important question. So the question is, are they all equal? And let's just call them, let's just say, for the sake of argument, yes, let's take them to be equal. And they all equal, let's just say O for simplicity. So they're all equal and they equal this operator O. So they're the same CFT operator. We're going to assume this for the sake of argument. This leads to a problem. Because if they all are equal, we know, for example, that OAB commutes with all operators in C, right? Because it's not supported on C. And then OBC, right? This is an operator just with support on B and C, commutes with all operators on A, and likewise OAC commutes with all operators on B. So if they're all equal, and they all equal this O, then we learn that O commutes with a general CFT operator. So I'm going to write phi, capital Phi CFT is like a general local operator in the CFT. So it commutes with all operators in the CFT. This is an issue because there's a theorem in group theory that applies here called Schur's lemma. And Schur's lemma says, is there a question?
Sorry, just a question. How are you sure that like the support is only in BC? Well, you definitely define it like in BC, but couldn't you extend it to the whole region?
Yeah, good.
In some way, I don't know.
Yeah, good. Yeah, so, right, you're saying just because we know we can reconstruct phi on say AB, we can also do a reconstruction on ABC.
Well, we can reconstruct it on AB,
Yeah.
but maybe there's some way where we can extend it to C that it will like still be compatible to what we did to AB. I don't know. I'm just wondering. It's not obvious to me why
Good.
I must impose that the support must be 0 outside AB.
Good. So the logic here is that you know, maybe there is a way of, you know, extending this operator so it does the same thing, but on A, B, C. Mm-hmm. But we don't have to do that. The idea here is that because we can just reconstruct it on A and B, we're free to say, okay, this is one form of the operator,
Okay.
and then that's how we're going to derive the contradiction.
Okay.
So if both are
You're free
possible,
to say that.
the fact that this is possible is the problem.
Mm-hmm. Okay.
Yeah. So, yeah, this is a good question. So with Schur's lemma, so Schur's lemma is the statement here that if O commutes with all local operators in the CFT, then O must be trivial. O must be proportional to the identity acting on the CFT. Yeah.
I don't really see why we had to go through this proof with Schur's lemma. If OAB, for example, we can write as a tensor product of operators on on A and B, tensor with the identity on C.
Yeah, you're saying like just look at them.
Yeah, exactly.
Yeah.
Like OBC doesn't have the identity probably on C, and OAB does, and you know.
Right. This is more rigorous.
I like proof by just look at them. When they. Thanks.
That's morally right. Yeah. So, right. So the idea is if under this, if we assume that they're all the same operator in the CFT, then they would be proportional to the identity, because just look at them. And then that is that okay? Is that consistent with our expectations of how the bulk is related to, is encoded in the boundary? Should its operators all be proportional to the identity? And I say no, because there's many problems with that. I mean, if every bulk operator is trivial, it doesn't really give you the same algebra you expect of bulk fields, right? So for example, this phi has some conjugate operator in the bulk, pi, let's say, and phi and pi don't commute. But we could have reconstructed both of them on the boundary, and by this argument, both of them would have to be proportional to the identity, and therefore they would commute in the boundary, and so we haven't preserved that algebra. So the idea is that this is a devastating contradiction. So this assumption was wrong. They're not the same operator. They're different operators. Okay, so they're different operators, fine. What does that mean? Can we just accept that and move on? Well, there's still this issue we have to wrestle with, which is that we have 3 different operators purporting to be the same bulk operator. How can they be the same but different? The resolution is that we should really, basically to jump ahead, we should really only expect them to be the same on this subspace, on this fixed QES subspace. So, there's no contradiction if we just assume that they act the same on the subspace that we were guaranteed they work on. If they were just guaranteed to reconstruct phi on that subspace, that's okay, right? Because you can have operators that all look the same on a subspace, but are different as operators, right? They act differently on the other states in the Hilbert space. So in that sense, they can be the same bulk operator, but different overall. And then the lesson would be that the bulk is encoded in the boundary. It's encoded in a subspace of the boundary. And the subspace is called code subspace. We saw this when writing the theorem because we wrote it as H code. So the lesson here, I'm going to say it this way. The slogan for this lesson is that we should think of the bulk as encoded in the boundary in a code subspace. The bulk is truly thought of as a code subspace of the boundary Hilbert space. It's not, and so bulk operators, when you map to the boundary, there's these many different ways of writing them on the boundary because these operators will all look the same on the subspace of the boundary Hilbert space, but not overall. Okay. All right. So these fixed QES subspaces are encoded in the boundary Hilbert space, the CFD Hilbert space, like a quantum error correcting code. Okay, I haven't told you what a quantum error correcting code is. I'm not going to go into great detail, but let me motivate the idea of why it's called this. Yes.
What is the status of this result if 2 subregions have a intersection region that is not 0?
Okay, yes. So to make this argument, we explicitly restricted our attention to these subregions that were disjoint. You could consider a C prime that was like this, and then.
Then what will be the reconstruction look like? I mean, because.
Yeah, there will be some reconstruction still on BC and still on. So the argument would essentially go through, even with these regions, because phi is still not in this C prime. So it would still go through unchanged. So, and you can do the same argument for different A, B, and C that you've rotated or made different sizes. It's very robust to
No, so my question is that here the idea was that the operator can be different as it is working on different subspaces. And as long as it is working on different subspaces, it really doesn't matter if it is kind of different prescription, I mean, or it has a different form. But if there is a common region between B and C, then in the common region, will not there be a conflict?
Good. Okay, yeah. Okay, good. Thank you for the question, because I want to make something. I want to clarify some language I used. So when I say these look the same on a subspace, I mean there is a subspace, a Hilbert space, which is a subspace of the CFT Hilbert space. And these operators all act the same on this subspace of the Hilbert space. I don't mean a spatial subregion. Does that help clarify? So yeah, so these operators are acting the same when you act them on any state that with support just in the subspace, but they will not, in general, act the same on a general state from this full Hilbert space. Does that help? When I say subspace, I always mean of a Hilbert space. Yeah.
So yesterday you mentioned that the FISQS subspace is a subspace of the code subspace. Can you clarify now what exactly do you mean with that?
Yeah, good. So historically, I think code subspaces were taken to be fixed QES, what I'm calling a fixed QES subspace. Those were considered to be what code subspace meant. They're like, okay, a code subspace is like a fixed QES subspace. I think that now we're able to sort of generalize away from that perspective. That the reason people said that was because the only theorem we had was this Theorem 1 that we've been proving. And H code there, the only one we could make sense of reconstruction for, was one of these fixed QES subspaces. So H code and fixed QES, historically, when Theorem 1 was all we had, they were identified. What we're going to see next lecture is Theorem 2, which is basically, it's the same thing, same idea as Theorem 1, but it drops the assumption of a fixed QES subspace. It keeps code subspace. So we're in our code subspace, so we're going to be able to talk about code subspaces, where the bulk is still sort of encoded in the boundary, like a quantum error correcting code. But different states in the code subspace can have different quantum extremal surfaces. And so when I said what you were mentioning last time, I imagine fixed QES subspaces. You can think of them as very small code subspaces, or like a subspace of some larger code subspace.
Thank you.
Okay, so okay, yeah. So what is this terminology, quantum error correcting code? Like how does that have to relate? How does that have to do with operators that work in a subspace and not generally, not on the full Hilbert space? Well, the idea is that the errors. All right, so the fact that you can reconstruct phi on, say, B and C without A is like you are correcting for the erasure of A. You still have the ability to write down this operator acting on the CFT Hilbert space, even if A were erased. So you've corrected for that erasure error. That's the connection that was made between this reconstruction and quantum error correction that people talk about in quantum computing theory. That's really what I'll say about quantum error correction. People use that terminology all the time. So we're going to have to get used to it. It's good. I mean, I don't want to bash it. I'm just saying that I'm not going to reference it that much, but it's important to know the history. Okay. Good. So next time, what are we going to do? Right, because we've established that we understand reconstruction in these fixed QES code subspaces, because subregions can reconstruct operators in their entanglement wedge there. But we know that we can't trust that these operators, that reconstruct the bulk operators, we can't trust they work outside of these small subspaces. Which is kind of unfortunate. I mean, it's unfortunate because, as I'll show you at the beginning of next lecture, a lot of the interesting physics, the bulk, doesn't fit into one of these fixed QES subspaces. So if you want a black hole, as Brian explained a lecture or two ago, those you can think of as having pretty large Hilbert spaces, like Hilbert spaces of dimension e to the a over 4g, where a is their horizon area. And you can ask, if I just have some black hole and some just like general black hole state, maybe a black hole I formed from collapsing a star, at some state in this large Hilbert space, and I want to talk about reconstructing operators on that black hole because I'm interested in understanding black holes. Can I do this all within some fixed QES subspace? And the answer for, if you just take a generic boundary region B is no. If you just took some boundary region B that was like some 70% of the boundary or something, generally, black holes won't fit into a fixed QES subspace like that. And this is very important because we want to understand reconstruction of black hole operators, but they're not governed by subspaces that Theorem 1 applied to. Okay, and I'll argue that more carefully to you at the beginning of next time. So that's going to lead us to trying to understand bulk reconstruction generally, outside of just fixed QES subspaces. So we'll write down a Theorem 2, which will look a lot like Theorem 1, but generalized away from that assumption. And then we'll discuss it. We'll understand what it says. And that's next time. Thank you.
All right, thanks. Any last question or two?
So this area term in the entropy that you found, when you have the semi-classical regime in the bulk, we know it's an area. When we don't have the regime anymore, like the CFT is not strongly coupled or like it's not large n or something, is there an understanding of what that A represents for like long strings or like no smooth geometry? What is that A?
Yeah, so I can interpret your question in two directions. One is, so we have this theorem and then apply it to ADS-CFT away from this like strong coupling large n regime. To the extent that it still satisfies the assumptions that there is this, there's this map V, there will be some, the theorem will still hold, right? Like, so if, but you have, that's a good question. Like if the theorem was a statement of equivalence between two statements, which are either both true or both false. And so if, I'm not sure exactly what A would apply to. I think with small stringy corrections, we do know the answer. It just applies. It's like the area, but with these like extra terms that, like the walled entropy and the Dong entropy, what they add to it. With large stringy corrections, the area, the QES itself might not have a very well-defined position, and then I'm not sure if the entanglement wedge is perfectly well-defined. And then it might even, you could get to a point where condition 2 wasn't even
I see. So you're saying maybe subregion duality is only valid in the semi-classical limit.
Perhaps. I mean,
yeah,
there might be
I
some
see.
generalized notion of it that still holds, and then this theorem would still apply. And I'm not sure what A would be exactly.
Okay, cool. Thanks.
Back to the stone regime. The definition of the area was for every big B and small b.
Can you say that again?
I'm asking if the area, the way you defined it, the entropy of chi, is for every big B and small b. And then what would it mean in general?
For every big B and small b, you're
Yeah.
asking? So, yeah, good. So the area in Theorem 1 doesn't, it depended on capital B, but it did not depend on little b. Because, well, it did, but little b was the same for all states, right? So little b was something fixed, And so capital B was fixed in the assumptions. So this area, while technically it depends on both of them, it was just this one number. I don't know if that's clear. Probably we'll be able to sharpen what you're asking when we see Theorem 2, where we'll have an area that explicitly depends on little b.
I didn't mean the state on B, I just meant that does it depend also on the way you separate the bulk into two regions? They code into two subspaces?
It does depend, yeah, so yes, it does. Except one thing to keep in mind is that in the assumptions of the theorem, this little b was fixed. So yeah, you wouldn't be able to, right? So it is the region that satisfies both of these conditions. If that makes sense. Say again?
But you don't need the reconstruction assumption for the definition of the area term.
That's right. You could talk about a generalization of this area that works for an arbitrary region. And in fact, we're going to define exactly that next time, because that's what goes into Theorem 2. But here, we didn't have to talk about an area for any different region, because there was only ever one area that showed up in the statement of the theorem.
All right, let's thank Chris again and go eat.